Hi guys, welcome back. Today we are going to learn about SPI communication, and in this tutorial we will see how we can program the SPI communication. So let's get started. SPI communication is basically a serial peripheral interface, and it's a full duplex communication. It was developed by Motorola company in late 80s. It can be used to communicate between two devices on the same PCB, and some people have tried with the 4 or 5 meters as well, but I won't recommend you to use it with the long wires because it's mainly developed for on-chip communication, and it's basically for microcontroller to sensors communication, and it's a very fast communication. It can support up to 8 megabits, and in some other devices it might support more, but in nRF devices we have 8 megabits per second as the fastest rate for the communication, and it's fairly easy to implement, and it has high transfer rates, and it's mostly suited to applications where you are acquiring data from sensors at a very high rate. So for example, if you are reading some ADC data at a very high rate, you can use SPI communication instead of TWI, because SPI communication is very fast and it's good for transferring a large amount of data. Let's see how we can use SPI to communicate between two devices. SPI is basically very simple to implement, but you have to keep in mind that MOSI is there are 4 pins, and basically for the data transfer we have 2 basic pins, which are MOSI, master output slave input, and MISO, master input slave output. These pins will always be connected in a proper way. If you are connecting MOSI with MISO, like in serial communication, it's going to be a big trouble for you. So make sure you connect MOSI pin with the MOSI pin of slave device. So in SPI communication, 2 pins are used for data transfer. One is for transmission and one is for receiving, and it's also based on master and slave communication strategy. So we use the master is always responsible for transferring or initializing the data transfers, and it also has its own serial clock pin, which is going to transmit serial data signals. These are basically serial clock signals which would be transmitted to the slave, so that slave can use these clock signals to receive the data. And the 4th pin is the CS or SS. SS means it's slave select, CS means chip select. It means the same. In some devices we use CS, and in some devices we use SS. Basically this pin is the same, and it is used to connect between slave and master. And in this communication, basically we don't have addresses. So to communicate with a slave device, master is going to pull its slave device line to logic low or high level depending on the settings, and so it's going to work in that way. Here is a simple circuit diagram to see the master with the multiple slaves. For example, you have slave 1, 2 and 3, and you want to communicate with them using your nRF device. Basically you have to have multiple SS, which are slave select lines for each slave, so that whichever line you will select, it's going to communicate with the slave device. We can connect with as many slaves as we want, but we need to have multiple slave select lines. It's easy to implement as compared to the addressing scheme like in I2C or TWI communication, and it's very fast, and it has no response mechanism. Like if you have transmitted some data, you won't be able to get an acknowledgement signal back like in I2C communication you have seen. But it's very simple to implement, and it's very fast, so it's mostly used with the flash devices or high-speed accelerometer and some advanced devices which need a lot of speed. Let's see how SPI communication works. So in this we have 4 modes. Basically we mostly use SPI mode 0 and SPI mode 3. We basically set the behavior of the data reading and writing. So normally we use mode 0 and 3, and for example, if we have SPI in mode 0, if we set the SPI in mode 0, here you can see it says active high. So what does this active high means? It basically means that the clock signal starts from logic low state, and the data transmission occurring during the rising edge of the clock. So basically when you are going to when the clock is going to go in the rising state from 0 logic to logic 1, you are going to read 1 data bit, and similarly on the next level it's going to go in the logic low state, and once again when it goes back to logic high state, you are going to read another bit. So basically you can read data bits by setting this up in any way, because some of the devices have different SPI modes. You can check out your data sheet, your device's data sheet, to see which SPI mode you need to communicate with. So we can set that in API of nRF devices. So we will see that later on. So let's see how it works. So basically in the start, the master is going to start the clock signals so that the communication can start. So here you can see the SCLK line. It has some clock signals, logic 1, logic 0, and these are going to be transmitted at a high speed, which is basically the speed we set like earlier. We said it can support up to 8 megabits. The clock will be set according to 8 megabits and per second, and here you can see we have these clock signals. So once the master is ready to communicate with the slave device, first of all it's going to generate the clock so that slave can be ready, and now it's going to set the slave select line to logic low level. It's normally in logic high state, so it's going to pull it low so that the communication can start and the slave device is ready to communicate. And this communication is basically a ring buffer communication. For example, if you transmit some data to slave, for example, if you are transmitting 1 byte of data to slave, the slave is also going to transmit 1 byte of data to the master as well. So it works in both ways at the same time. But for example, if we are just writing the data into the slave, we will receive some bytes of data as well from the slave, but we will just ignore it. In the API we completely ignore that. It's automatic, so you don't need to worry about that. If the master is just transmitting, it will still receive some data, and it will be ignored by the API automatically. And if the master is receiving some data, it will transmit some extra data to slave as well, and the slave is also going to ignore that. And here you can see, for example, if we have set to active high state, which is mode 0, so upon every clock signal high state, it's going to read 1 data bit. So here you can see that when the clock is rising, you can read 1 data bit. Similarly, if you are in mode 3, what's going to happen whenever the clock is going to the logic 0, you will read a data bit around here. So it's just 1 step difference, and you don't need to confuse yourself with this. It's mostly automatic. So for the beginners, I will recommend to just cope up with this stuff. It's very simple. If you continue to try this communication for some time, you will get to know how it's working. So don't worry, and just program it as I do it, and then you can easily communicate with some devices as well. Okay, so let's see how is the structure of our nRF52832. We will see the structure of both devices, nRF52832 and nRF52840. So first of all, let's see the structure of nRF52832. We have 3 SPI instances. So for example, if I need to communicate with 3 different slave devices on 3 different lines, I can use 3 different SPI instances. For example, I can use SPI instance 0 for communicating with the 5 or 10 slaves or 2 slaves or whatever, and I can also use SPI 0, SPI 1 and SPI 2 as well, and we can use multiple SPIs because we have 3 SPI instances available in the nRF52832. We can also allocate the different signals to different pins. For example, I can allocate MOSI to any pin, MISO to any other pin in the microcontroller available, and we can use them in any configuration as we like. And we have 3 different types of SPI modules. Don't confuse yourself with them. In TWI we also saw that we have different types of modules. So what are these modules? For example, in SPI instance 0, we have SPI, SPI-M, and SPI-S. So basically SPI is simply serial peripheral interface, and it does not involve EZDMA. So it's basically for basic communication in which you want to use blocking functions. If you are using that, you can then you can just simply use SPI communication. And if you are using non-blocking communication and you are using EZDMA, or you are just using interrupts based on EZDMA, without EZDMA you can use SPI-M, which is SPI master, and we can also use SPI slave if we want our nRF device to act as a slave device. But make sure you only use one module of each instance. For example, if I'm using SPI 0, then I cannot use SPI M0 because SPI 0 is already being used, so it uses the same address, so these two modules won't be able to work. Although I can use SPI M1, which would be the instance 1, and I can use that. You can use different modules, and also keep in mind that SPI also shares its base address with TWI. So if you are using, for example, if you are using SPI 0, then you won't be able to use TWI 0. So you have to use TWI 1 instance instead of SPI 0, and but not both at the same time. In nRF52832 we have SPI 0, SPI 1, and SPI 2, so we can use them. And I will also let you know where to check in the datasheet, like which addresses are overlapping, so that you can know which modules or which instances you can use at the same time. Here in the architecture of SPI, it's very simple. We are just going to declare some buffer in the RAM, and the EZDMA. It's very easy to enable the EZDMA from sdkconfig.h file using the CMSIS configuration wizard, and it's automatically going to handle all the stuff for us. And this is the basic structure, and we can see we have 3 pins, and there is no chip select pin mentioned here. We can just use any pin as chip select pin, so it's not a big deal. So let's see nRF52840 architecture. So it's a little bit an enhanced architecture, and here in nRF52840 we have 4 SPI instances available, and each instance has a SPI, which is simply without DMA, and SPI-M, which is master, which can even use DMA, or without DMA it can still work. Basically these are non-blocking SPI modules, so SPI-S and SPI-M, whereas SPI is basically a blocking module because it waits, puts the processor in the wait state until the communication is finished. And make sure only one module can be used at the same time, as I have discussed in the previous slide. So we in nRF52840 we also have the same stuff here as well. And for example, here I have created a simple example to let you guys know how it's working. So SPI instance addresses might coexist with other peripherals like TWI. So for example, SPI M0 and TWI-M0 share the same base address of 0x400300. Basically in this case only one instance would be able to work, so you have to either use SPI-M0 or TWI-M0. If you are using SPI-M0, then you won't be able to use TWI-M0, although you can use TWI-M1 or TWI-M2 depending on your conditions. You can use any other. So where do you find these addressing and all the stuff? Just open the datasheet of nRF52832 or nRF52840. Look into the instantiation paragraph. So there you are going to find these addresses which are similar for some modules. So you can see you can use which modules upon activation, and which modules are sharing the same base address. SPI in nRF52840 works in the similar way as in nRF52832. The only difference here you can see is the CSN, which is a slave select pin, and also we can see DCX pin. The DCX pin is new for some new devices, and it's an advanced feature. Basically, we can also implement this in nRF5 2832, so don't worry. This DCX pin is basically a simple pin which is going to show whether the transmitted data is a byte or a command. So for example, if the DCX pin is sending the is set to logic low level, then it means the byte transmitted during this time is basically a command, or it may be data depending on our settings. Okay, so it's fairly easy to implement. We don't need to know all of the internal structure of the device. We can just simply learn the basic API, and so we can use it to communicate with any sensor. So next we are going to create a simple program, and I will be using a sensor, and we will just see its whoami register, and see if its register give us the same default value as mentioned in its datasheet. If it gives us the default value, then it means we are communicating with the right device. So here in this type of communication, you are seeing that we don't have addresses for the slave devices, but keep in mind that we have to transmit a register address, then we will read the content of the register. So for that we have some commands, so we will see that in the coding. I hope so everything is clear. SPI is simple to implement as compared to TWI, and it's very fast, and if we see serial communication, SPI is still faster than serial communication, so it's mostly used in high-speed communication devices. And later on in the future tutorials, we are also going to see QSPI, which is quad serial peripheral interface, which is more faster and which can be used with some high-speed devices as well. Okay guys, so let's program it and let's see how it works. Okay guys, today I will be using this sensor which is basically an accelerometer, and it's from ST Semiconductors, and the sensor's model is LIS3D-SH. Here we can see it has some pins, and I have connected these pins here. In the next tutorial I will be using a library, and I will explain the communication of LIS3D-SH, but right now we are just seeing the basic stuff, so I'm just gonna explain the SPI programming for the basics. So let's get started. So I will be using this sensor as an example so that we can see how it's communicating with a real sensor, so that we can see how the SPI communication works. Okay guys, so we are going to create a new project. So first of all, go into this PC, and here in the C directory we have nRF SDK, and if we go into the examples and then go into the peripheral, we are just going to copy this SPI from here and go into my projects, just paste it here, and let's open this SPI. And I'm using nRF5 2832, so I'm just gonna open this PCA10040 and then open this blank, open SCS, which is Secure Embedded Studio, and then open the EM project file. So first of all, I'm just gonna remove this code, and I'm just gonna zoom in a little so that you can see everything. I will remove all the stuff so that we can start from the basics, so you can see how it's working, because today's topic is on the SPI, and I want you guys to grasp the basic concepts and how to use the API to communicate with some external sensors. So guys, we are going to create a simple SPI communication. We are just going to use LIS3D-SH sensor, and for that in the datasheet of LIS3D-SH we have some stuff, and I'm just gonna define that. So this is the address of register, okay guys, this is the address of the register in the LIS3D-SH sensor, we will just write this register address, and then we are going to read the value from it. If its value is equal to 3F, then it means we are communicating with the right sensor. So I'm just gonna use these constants, because they are similar in the library as well. So later on in the next tutorial we will see that. Also, we need to define the buffer size for SPI communication, because I'm just communicating by transmitting 1 byte at a time, so I'm not gonna use a very high buffer size, and let's set it to 8 bytes. Also, let's say SPI instance. We are using SPI instance 0. And there is one more thing, because we have to tell that we are reading from the SPI. So for that we have a specific command, and we are just going to use a special defined function. Later in the next tutorial we will see this in more details. So basically whenever I'm just going to pass a register to this function, it's simply what it's gonna do is it's going to use logic OR with that register's value with 0x80. So it will transmit it, so it means we are reading some data. I will explain this in the next tutorial. Right now we are just going to see the basic communication, so we will not go into too much details about this. Now I have created a TX buffer and RX buffer in which we are going to send or receive the data. Basically we are just making these buffers in the RAM so that we can read the data in the buffer, and then we can use it, or we can just transmit the data via buffer. Make sure you create these buffers in the start of the SPI communication program. Also, we need to set a flag for the transmission completion. Okay, the next thing is we have to create an instance. Now we have created the SPI instance, and the next thing is we are going to create a simple initialization function for the SPI communication. Okay, we have just called the default configuration values, and now we are just going to set the stuff from this default configuration. So I have set the communication rate, communication speed to 4 megabits per second. Here we have to pass the event handler, so we have to create the event handler first. And here in the event handler we are just gonna set the flag to true, so that it shows that once the transfer is finished, this is just going to set the flag to true, which will show that the communication is finished now. Communication has completed now. So the next thing is we have to write a simple function which is going to write some data in the register of LIS3DSH. So for that I'm just gonna make a new function. and here I'm just going to call that read command, so that the passing register, because we are just reading the data, so I'm just passing it a register so that it can create a read command for that. We will set the flag to false because now we are starting the communication. So it's going to wait here until the transfer is completed, because once the transfer is completed, this flag is just going to get true, and once it's get true, this while loop is exited, and the next command is then executed. So here in the next command we are just going to return what we have read in the buffer from the register. That's it for reading from a register in LIS3DSH. So it's finished. Now let's go into the main function and write some basic code for communicating with the device. We are going to read the default who am I value in a variable. For that I'm just going to create an integer. Let's initialize the logger so that we can see the log messages in the serial port. Let's initialize the SPI, and then let's pass display a simple message. And now we are just going to read the value from the LIS3DSH sensor, and we will pass it the address of whoami register so that it can read from the whoami register. And if this reading, if the value of this register is similar as mentioned in the datasheet of LIS3DSH, then it means we have successfully communicated with LIS3DSH, and we have read its register using SPI communication. Okay guys, the code is completed, and let's build the code. Oops, I forgot to mention this event handler here, so I'm just going to copy this. And we will pass it a null value in the end. And I'm just going to close this. Okay, it's good to go. This was a little mistake, so make sure you don't make it. Okay, it's finished, and make sure your device is connected. Go to the target, click on the connect with the target device, erase all, and then download this code. Make sure the other serial to USB converter is also connected so that you can see the data over serial port. So for that I will be using the PuTTY terminal. For before using the terminal, I will see which port is connected. So I will go into this PC, then open the properties, go into the device manager. I'm just going to close this, and here in the port you can see the COM9 port is connected. So I will just close that, open the PuTTY terminal, go in the serial, put the baud rate to 115200, and let's say the COM port 9 here, and we are just going to open this. And one thing I forgot to mention, that since we are using nRF logger, and we are not using the power management, so go into the SDK config.h, open the CMSIS configuration wizard, go into the logger. Here in the logger we have deferred enabled, and just disable this and save it. Now it's good to go. Just build it once again, and then connect with the target, erase all, and then download it. and once you have downloaded, you can see the log message. It says that SPI application is started, and then the who am I value is correct for LIS3DSH. It means it's successfully communicating with this device using the SPI communication. So that's it for today. I will make more useful tutorials for you guys, so make sure you guys support me. I hope so you have learned something new today. The code along with the information is available for download. Please be sure to check it out. And if you are new to my channel, please be sure to subscribe to my channel and hit the like button if you like this video. And the LIS3DSH sensor has a lot of features, and we are not going to discuss everything, but in the next tutorial I will just go through some basics of communicating with the LIS3DSH sensor using a proper library, not like this. And I hope so you like this tutorial. Thank you very much for watching. See you in the next video.